Okay, today we're going to do an independent groups t-test. And you would use this when you have two different groups of people. So we can think of this as essentially a between subjects, between groups design. What we're going to use for our example today is people with unilateral versus bilateral brain damage. And we're going to give them a perceptual task, and then we're going to compare and see how they do on them. So we're going to call this N1. We have 12 people with unilateral brain damage, which means brain damage on one side of their head. The mean on this perceptual task for them is 49.19. Their variance for their group is 74.65. I should have given myself more room. The standard deviation for this group is 8.64. For the bilateral group, it's tougher to find people with bilateral brain damage, which is damage to both sides of their brain. So we only find 5 of them. Actually, it's easy to find people with bilateral brain damage. They're just usually in the ground. The mean for that group is a 38.43. The variance for the bilateral people, group 2, is 49.28. And the standard deviation, is equal to 7.02. Okay. This is essentially hypothesis testing. And so we have to set up a null and alternative hypothesis, and then we're going to do a standard error, and then a t-test, degrees of freedom, and then check this against our critical value. Okay. So our null hypothesis is going to be that mean 1 minus mean 2 is equal to 0. So in other words, there's going to be no effect for unilateral versus bilateral brain damage. The alternative hypothesis, H sub 1, is going to be that mean 1 minus mean 2 is not equal to 0. So we're making a bidirectional statement. We're not saying greater than or less than. We're just saying it's not going to be equal to 0. Okay, since we have all of these numbers already for us, like mean, variance, and standard deviation, we can skip right to standard error. And standard error, the formula, it's little x bar 1 minus x bar 2. You could think of this as an omnibus variance term. Well, actually, really an omnibus standard deviation term. The formula is n1 minus 1 times the variance for group 1 plus n2 minus 1 times the variance for group 2 over n1 plus n2 minus 2 times 1 over n1 plus 1 over n2, all under a root sign. So, like all statistics from here, all we really need to do is fill in the numbers. So n1 is equal to 12, so we can put 11 times the variance for group 1, which is 74.65, plus the n for group 2 is 5, so it's n1 minus then 2 minus 1 is 4, whoops, times the variance for group 2, which is 49.28. Holy moly. Over 12 plus 5 minus 2. Don't need a calculator to figure out that one. 1 over 12 plus 1 over 5. Keep it under the root sign. I'm going to skip a couple steps here, and I can tell you that this comes out to be 4.38. Okay, so multiply this out, divide by this, multiply times that, and there you go. Our next step then is to find t, and t is going to be equal to mean 1 minus mean 2 over our standard error. X bar 1 minus X bar 2. So plugging in those numbers, here's our mean over here. So we get 49.19 minus 38.43 over 4.38 to set that up. And our answer we come up with is 2.46. We need to get our degrees of freedom. So this is our t obtained. So we're going to be very interested in that number. Our degrees of freedom is equal to n1 minus 1 plus n2 minus 1. And so 11 plus 4 is equal to 15. From this number, we're able to get our critical value of t, and so we can get our t critical, which we look up, or I would provide for you. It's equal to 2.131. And what we see is that our t obtained is greater than our t critical, and so therefore we are able to reject the null hypothesis that there is no difference between people with unilateral and bilateral brain damage. What we can say is that statistically, people with unilateral brain damage do better on this perceptual task than people with bilateral brain damage. And that is how you do a independent group's t-test.